Good evening, my glorious students. So we're only going to have one video this week because one of our sessions is supposed to be reviewing for your upcoming test / playing catch up. So again, as always, anytime you would like to come ask me a question, Tuesdays and Thursdays, I hang around in the 1311 room. Being bored, please come by and make me not bored by asking a question, please. All right. So what we are looking at right now is radical equations. Coming up, well, one, we see these sometimes when we're solving some of the weirder functions or graphing them. The square root of x, cube root of x are also basic graphs that you have to know about. And they're actually the more common ones for, like, take the square root of x, then shift it up, shift it right, flip it, stretch it. What's the equation of the graph? It's pretty standard to use square root of x for that. All right, so for a radical equation, anything that has a radical, it doesn't matter what the index is a radical equation. And the way we eliminate the radical is by raising both sides to the power that matches the radical. So like here, it's a 3. There we go. And so both sides got raised to the third power. But here's the catch. Whenever you raise both sides of an equation to a power, you introduce the possibility of extraneous solutions, meaning some of the solutions to the equation may not be solutions in the original equation. And it in fact is possible to have no solution at all, even though you did all the math work and you got a solution, it just does not solve your original equation. Like check out the straightforward example here, square root of x equals -10. Hopefully you look at that and go, wait a second. Because normally, if we don't see a negative in front of the radical, that is indicative of being the positive root. So if I put 100 in there, square root of 100 is +10. We don't do plus or minus when the equation gives us the square root. Only when we write the square root do we put the plus or minus. That's why I kept saying that when we were solving quadratics, using the quadratic formula and whatnot. If it starts with a radical, then what we see is what we get. So here, the original equation, square root of x equals -10, we square both sides, we have x equals 100, which makes sense, it just doesn't solve the original equation. So this is perfectly correct work to arrive at solution set is the empty set or no solution. So I've got 4 different examples that we're going to run through, and I'll just post it as one nice video. So overall, the steps for solving a radical equation are the same. It doesn't matter what the kind of radical is, how many there are. You get one of the radicals all alone, meaning there are no terms outside the radical on that side of the equation. Then you raise each side to whatever the correct exponent is. Almost all of these equations can be a square, unless it looks like really perfect when you isolate, basically. Then you solve that equation, and then note here, if it still has a radical, do it again. Isolate that radical. Then raise both sides to a power and then solve that equation, because then the radicals should be gone. Check the potential solutions in the original equation and write the solution set. So if the equation has a solution, it will be one of the solutions you find to the, I think of it as the bigger equation, just because usually when we raise it to an exponent, like, things get bigger. Now this makes a note about, technically you only have to check it when you're raising it to an even power. That's true, but honestly, I just check all the answers. And this is kind of the point in math where you start checking all the answers, because now we are going to do things to both sides of the equation that introduce the possibility for extraneous solutions. When we take natural logs, or when we undo natural logs and regular logs, those introduce the possibility of extraneous solutions. If you guys are going to go into pre-calculus, a lot of the trig functions introduce the possibility of extraneous solutions. All right, so just like here to the end of math, get in the habit of checking. Now you don't have to like, oh my God, write a whole long check step. You can just like crunch it in the calculator. Does it work? Yes, cool. All right, so our first example here. We have the lovely square root of 7x plus 8, then a minus 2 on the outside, and this is equal to just x. So I'm going to zoom in a little bit because y'all know my handwriting's huge. So first step is, I know it's a square root. I know we want to square both sides. Before we square both sides, we need the square root by itself. If I squared this right now, this would be an ugly FOIL with the square root and the minus 2. You don't want to do that if you don't have to. So we're going to add the 2 first. Because remember, square both sides does not mean square each term. You have to square the entire side. So this is going to leave us with the square root of 7x plus 8 by itself and x plus 2 on the other side. My square root is by itself, so now I can choose to square both sides. I always do this by writing my lovely parentheses. Safe math. When in doubt, write them anyway. The left side, square root and square are going to cancel, and we now just have 7x plus 8. And on our right side, x plus 2 whole thing squared is a FOIL or a box method. So I'm just going to shortcut that process a little because I've done way too many of these. Or also thinking to our completing the square thing, I double this number with the variable. So positive 2 times 2 is positive 4x. And then I square it, which also gives us plus 4. Only one to do that. All right, now I have a quadratic, which is why we spent so much time solving quadratics. We're going to get these coming out of some of the log and exponential equations. Just a lot of the math problems end up devolving back into a quadratic. All of them work with the quadratic formula. So I'm going to move this 7x over and the 8 at the same time because I'm lazy. I just lined them up with their like terms. So I have my x squared. 4x's minus 7x's is negative 3, still an x. Positive 4 minus 8 is now negative 4. Now, here's the catch on these. Most of them will factor because we don't want you to have to check an ugly square root number. We want you to be able to check with a nice pretty whole number, or integer at least. Sometimes you might get a very simple looking fraction, but again, that would come from a factored polynomial. You can still use the quadratic formula if you just don't want to think about it, or you've got a faster way on your calculator, do that. But expect these to factor is what I'm saying. Expect to get integer answers. So if you don't get an integer, then you kind of take a step back. Is that on purpose? You know, unless, and it might be, but if you go through the quadratic formula and then get imaginary, it's like, oh, that's why, because there's no real answer at all. All right, so dropping down the parentheses, and this is our lazy factoring. So I just need to pair that. Multiply to negative 4, add to negative 3. There's not a lot to choose from. So a negative 4 and a positive 1 will do it. Those are the numbers inside the factors. Those are not the solutions. Of x plus 4 equals 0, so x is negative 4 is one of our potential solutions. Now gut instinct might be, oh, it's negative. I can't have a negative inside the radical, which is totally true. But we do sometimes get a negative solution to the radical. It would also help if I actually solved the correct equation. Thinking too many steps ahead. X minus 4 is going to give us the solution of x equals 4. X plus 1 is going to give us the solution of -1. We need to check both of those. Do not just chuck out -1 because you're like, oh, there's no way that'll work. It will work. Maybe. We'll see. All right. Now, when you check your work, go back to the very original equation. And I kind of think of this as go back to the one that I didn't have to start with writing. That's either printed in the book or printed on the screen. Now, part of the reason that we get these integer answers is it makes it easier to check them. But you can always just crunch this in the calculator. So my first step, I just substituted in the number I'm checking. And that gives me like something that I could type on the calculator if I want. Or if it's not as ugly to crunch, then I will just do it by hand and figure it out. So our first one is 4. So everywhere there's an X, I'm going to put a set of parentheses. I'm going to rewrite the rest. And let's put those numbers in. So now we are checking 4. So 7 times 4, 28. 28 plus 8 is 36. So we tentatively have the square root of 36 minus 2. That is 6 minus 2, which is 4, which does indeed equal 4. So x equals 4 works. Yes. This doesn't mean check out the other solution. Check them all. Sometimes they will both work. Sometimes neither will work. Sometimes it's only one. Most of the time it's only one, but sometimes they both work. All right, so now we have 7 times -1 plus 8 minus 2 equals -1. Let's see what we get. So 7 times -1 is -7. -7 plus 8, though, gets us back to a positive. So this is square root of +1 minus 2. Square root of +1 is 1. So we have 1 minus 2, which does indeed equal -1. So both of these numbers do in fact work. They are both the solution. Now on ALEKS, you are probably going to be asked to write it as a solution set. So we just drop down the curly braces and then you just list the two numbers. So 4, -1 or -1, 4. Do not put parentheses. In fact, ALEKS will usually type the curly braces for you. So all you have to do is the numbers with commas in between. That's it. There will also be an option on all of these for a no solution because it can happen. Just depends on how the equation is written. All righty. So we isolated the radical, raised both sides to an exponent, solved it, checked our solutions, both worked, answer. Do it again. Now we have the very weird looking, but not always in math does weird looking mean bad. Sometimes it's okay. So let's see what we get here. All right. So I have the 6th root of y plus 7 minus the 6th root of 4y plus 5, which can be a little daunting. Normally, when you get 2 radicals, it means you're going to have to raise both sides to an exponent twice, which with 6th roots, ugh. But these are set equal to 0. When this is the case, and we isolate the radical, check it out. I'm going to add over. And now I have the 6th root of y plus 7 is equal to the 6th root of 4y plus 5. So this is what I'm going to solve. And since it's a 6th root equal to a 6th root, when I raise both sides to that exponent, It is the same exponent that cancels out the radical, so both the radicals are going to be gone, and we're going to be left with a nice linear equation to solve. Now, about the only catch is, the only way for this answer to not be horrendously huge is to end up with a fraction. Which, once I get a fraction answer, I'm like, calculator all the way for the check. That is the alarm to remind me that it is indeed trash day. All right, so y plus 7 and 4y plus 5 now. Radicals are gone. They will be there when we go to check this, though. All right, so I'm going to minus the y. And since this will now be just y's, I will move the 5 to the other side. So we end up with 2 equals 3y. See, fraction. Divide by 3. Y is 2/3. Or 2/3 is y. It doesn't matter which way you write it. So 2/3 right now is our potential solution. Might work, might not work. Don't know yet. So the check step. So we have here, and I'm going to write it with a whole bunch of parentheses. Actually, I'm just going to write it first, and then I'll write what you would type. So the 6th root of 2/3 plus 7 minus the 6th root of 4 times 2/3 plus 5. Now remember, 4 times 2/3 is not the same thing as 4 and 2/3. And then this is supposed to equal 0. Now you might be thinking, Liz, there ain't no 6th root button. I know. So there's 2 ways to go about this. A lot of calculators, if you dig really far in the catalog, you can find an X root button. Personally, though, when I want to type something like this, I just switch it back to the fraction exponent, which I know, why would you put more fractions? Because there's not a 6th root button. So in the calculator, now because we also have fractions in here, I like to put extra sets of parentheses around my fractions themselves. So here's how it's going to look. So I start with, I need that big set around the 2/3 plus 7, but then the 2/3 is going to get its own set as well. Now, a lot of calculators, in fact, all of the calculators, if you don't put that parentheses around the 2/3, it should still work because order of operations says do division before addition. But you do definitely need that big set around them. And then it would be raised to the 1/6 power. If you have that natural display, it's going to automatically move the 1/6 up top. So you'll still be on there when you do the divide by 6. So you don't necessarily need the parentheses, but it won't hurt to have them up there as well. But if you have an older TI, you're going to need those parentheses. Now, don't hit enter right now. I don't know what that is, but it's probably not a pretty number. Now we're going to do it again. So I got my big set, and then that will have the caret and the 1/6 in parentheses. And then inside here, 4, then my 2/3, and then my plus 5. Yeah. You might have to put a times between the 4 and the 2/3, but if you're using the type of calculator where you can type the whole thing in, you should just be able to type it exactly like this, hit enter, and it should give you 0. So I'm gonna, let's see, 7 and 2/3. Let's see, 3 times 7 is 21, 23/3. So that is what's inside the radical. I don't want to actually know what the 6th root of 23/3 is because it's not pretty. But here, this is 8/3 plus 5/3. Sorry, 8/3 plus 5. 5 times 3 is 15. 15 plus 8 is again 23/3. So these are indeed equal. We would get 0. So 2/3 is a viable solution. It's the only one we had, so it is our only solution. If it didn't work, when you hit enter, it wouldn't show you a 0. It'd show you any other number. Doesn't matter what the number was, just some other number. And that means the number you just checked doesn't work. That doesn't necessarily mean you're done, especially on one like this where it worked out to a nice, pretty linear equation. Odds are pretty good that number is going to work. So then I'd go back and check my original work. All right, so I'll go ahead and box that in because it is indeed the solution. Or we would put 2/3 in curly braces. That's what you call the wiggly lines, which are kind of a pain to write. So like for students, it's usually totally acceptable to just be like wiggly line, put your solution in there. Okay, maybe not wiggly 5, but. Or like me, you can spend your English class practicing writing curly braces. I just didn't like my English teacher. It wasn't English's fault. Then we get something like this. Yuck. I'm going to have to raise this to an exponent twice because I have a radical, another radical, and it's not 0 on the other side. So I'm still going to show you how this works. So I'm going to take the negative radical and move it over so it's positive, just so I don't have to think too hard. Plus the square root of 6 plus 2x. So I have one radical isolated, the square root of x plus 4. And on the other side, I'm going to write the radical first because it's positive. The square root of 6 plus 2x, and then the minus 1, because we are about to get an extremely funky looking binomial to multiply out. All right, so they're square root on the left side, so we're going to square both sides. Remember, it is the whole entire side, not each term. So certainly if I just did it to each term, I would get an equation that I could then solve, but I am not going to get the correct potential solutions, and then I will incorrectly end up with a no solution. All right, so the left side at least works out nicely. Square root and square cancel. We have x plus 4. But the right side, I'm going to go ahead and write the box for this because it's ugly. I don't like looking at it, but there it is. So we have the square root of 6 plus 2x and the minus 1, and the square root of 6 plus 2x and the minus 1. So the square root times the square root, since they're the same square root, I would get the square root squared, or just 6 plus 2x. And down here, -1 times -1 is going to be a positive 1. Those are nice ones. Then here, I'm going to get a negative square root and a negative square root. So I'm going to get the same term twice, which is very normal for a perfect square. So I get 2 of those. So on my other side here, I have 6 plus 2x plus 1. That's why I did those two first, because I knew we were going to have some like terms. And I'm just going to go ahead and combine that. So that is 7 plus 2x. And then it is minus the square root of 2 square roots of 6 plus 2x. All right. So I still have a square root after all that craziness. Now hold on, let me move this box method because it's a little too close to our work. There we go. So again, same song, second verse. I'm going to get the radical by itself. Now, if I move the 7 and the 2x over to the other side, I'm going to get a whole bunch of negative stuff. I don't like squaring with negatives, but I'm going to move them over, and then I'm going to divide everything by a negative number, by -1, sorry. That way all the signs flip back to positive and it looks nicer. You don't have to do it. You can square with the negatives. Like, it'll still solve to the same equation. I just don't like the way it looks. So -7 here and -2x here. So for the moment, I have a -1x, then 4 minus 7 will be -3. And then on the other side, I have the negative 2 square root of 6 plus 2x. Now, when we say isolate the radical, we mean isolate it from things that interfere with the exponent part of the problem, like raising both sides to an exponent. The 2 in front, the squared number and the radical actually, distribute across multiplication. So I don't have to get rid of the 2. I'm just choosing to get rid of the minus because I don't like the way it looks. So I'm just going to divide both sides just by a negative 1, the whole side, but that's going to divide into both of those. That is a really horrible arrow. All right. So now this is x plus 3, much nicer to look at. And now this is a positive 2 and the same radical. Now we're going to square both sides. All right, left side is going to be a binomial that works out pretty nicely. On the right side, the 2 is going to get squared and the square root is going to get squared. So that means the 2 squared will be a 4. The square root squared will cancel, and we are left with 6 plus 2x. But this was originally 2 times the whole radical, so it needs to be the result of 2 squared times the whole thing that was in the radical. Safe math. Over here, we got a quadratic. So it's going to be x squared plus double positive 3 is positive 6 with an x, plus 3 squared is 9. All right, so this is the equation I'm going to clean up. Give me a sec, I'm going to make myself some more room. In fact, I'm going to do that by moving the box. And then I'm just going to take this, rewrite it up here with the next step. So x squared plus 6x plus 9 equals 4 times 6 is 24. 4 times 2x is 8x. My x squared is positive on the left, so I'm going to take all the things on the right and move them left. Because I like the x squared to be positive. If it's not positive, it is a pain in the butt. Man, those numbers look ugly. So I still have my x squared, so if it factors, it shouldn't be too bad. Minus 2x, all right, I'm all right with that. And then 9 minus 24. 24 minus 9 is 15, but it will be negative 15. All right, not a lot of numbers to multiply to 15, so not that bad. In fact, I can really only think of 5 and 3. And since it's a negative 2x, I make the bigger number negative, the other one positive. Adds to a negative 2, multiplies to a negative 15. That is indeed our factored form. So our solutions, and after a while, especially since you solve so many of these, you get kind of tired of the whole x minus 5 equals 0, add the 5, x equals 5, and you just start skipping to the end. X plus 3 equals 0, minus the 3, x equals negative 3. Remember, we still have to check in the original equation. So I'm going to run through that down here. Give me a sec. I'm going to move this work a little. All right. So our first one is the ugly square root. This is going to be 5 plus 4, which your brain may be thinking 9. Yay, 9 square roots nicely. All right, this is already looking promising. Minus the square root. 6 plus 2 times 5, 10, 16. Ooh, 16 square roots nicely. Does that equal negative 1? Let's see. So like I said, square root of 9 minus square root of 16. That is 3 minus 4, which is indeed negative 1. 5 works. Now we just got to check negative 3. Now, if you're using the TI and you crunched it on the calculator, you can actually hit it's second and equals on a TI, and it will bring the previous line that you just typed in back up, and then you can go back to where you put the 5 in, you delete the 5, and then you're going to have to hit second insert so you can type in -3, because it'll only let you replace like one digit at a time. So the insert will allow you to put more than one character. That's the word I wanted. Okay, so we've got the square root of now -3 plus 4. Oh, well, that works out nicely. That's square root of 1, so that's 1 minus the square root of 6 plus 2 times -3. Oh, 2 times -3 is -6 plus 6 is 0. Square root of 0 is 0, so it does indeed equal the desired -1. They both work. That does not always happen. I kind of picked these problems at random as I was going through the end of the chapter section problems. I just happened to pick ones where they always worked. If it is not going to work, you're going to end up with something like -2 equals -1, or 3 equals -1, or 0 equals 2. Just a blatantly false statement. Something where the two sides are not equal, that means chuck that answer out. It does not work. Now you may see just a few problems in your homework where you're dealing with these rational exponents. Now it's good to keep these kind of in the forefront of your mind, because when we start looking at exponential and logarithmic functions, those are the functions that are going to help us get at those crazy exponents. So seeing an exponent as a kind of crazy number will help normalize that this can in fact be an exponent. And really any integer can be an exponent. All right. So 2x minus 1 raised to the 3 halves minus 3 equals 122. So that radical is hidden here, but that rational or fraction exponent is our radical. So I want to isolate the term that has that fraction exponent. So I'm going to move the 3 over. I'm going to zoom in. Now I'll move the 3 over. So I have 2x minus 1 to the 3 halves is now equal to 125. Now, 2 ways to go about this. And I did not check to see which way Alex does it. But we need to get rid of the 3 halves power. One of the ways to do that is to turn it into a 1. So I need to figure out what number do I multiply 3 halves by to get 1. Not add to it, multiply by. Or I can do it in 2 stages. I get rid of the fraction part first, then I'll get rid of the other part that's left over after we clear the fraction. I prefer to do it all at once because I don't like to do a lot of work, but you may have to type it into the calculator as 2 steps. So I'll cover that in a sec. So the number that I multiply 3 halves by to get 1 is 2/3. So 3 halves times 2/3 is 1. So in order to multiply an exponent, I have to raise it to another exponent. So we're going to raise both sides to the 2/3. Because remember, those two crazy fractions are now close enough to multiply. See, there's a reason I told you cheesy joke. It keeps coming back. So those multiply to 1, 2x minus 1 to the first power now is just 2x minus 1. So now we just got to figure out, how do I type 125 to the 2/3? One of the ways is to try 125 to the 2/3. And on the newer calculators, that should work fine. If you want to be extra sure, you can put parentheses around the 125, doesn't hurt. Some calculators, though, kind of flip out when this fraction isn't a unit fraction, meaning the number on top isn't a 1. So if you do this and your calculator is like, I don't know what to do. All right, take a step back. We will just break this up. So we are going to have this in 2 stages now. So one of them, I can either do the 2 or the 1/3, but this 2/3 is the same as 2 times 1/3. So I'm going to break it into 2 exponents. I habitually go with the fraction one first, but it really does not matter. And then afterwards, I will raise that to the 2. So that's an exponent to another exponent. But just so the calculator doesn't get confused by my chain of exponents, I put another larger set around the whole thing. And then, of course, our number would just go in here. Now, in this case, the cube root of 125 is 5. 5 times 5 is 25. 5 quarters is $1.25, so 125. So this is 5. So we really end up with 5 squared, which is 25. And now we just keep solving like a normal equation. Add the 1, add the 1. 2x equals 26 now. Divide by 2. And x is the weird, unlucky 13. But it's card number, so it's not horribly unlucky. And what do we have to do next? Check. Highly recommend the calculator for checking here. Like once it's more than square roots, my brain is just like, I don't want to think about it. All right, so at least it's an integer. So we have 2 times 13 minus 1 to the 3 halves minus 3 is supposed to equal 122. 2 times 13 is 26. 26 minus 1 is 25. So this is now 25 to the 3 halves. Now again, I'm going to break this up. It's 25 to the 1/2 to the 1/3. So if you're trying to calculate this by hand, this is the way you do it. 1/2 power is the same thing as the square root. 25 is the same as 5 squared. So the square root of 1/2 power and the squared cancel out. So this is 5 to the 1/3, which is 125. 125 minus 3 is indeed 122. All of our solutions worked. Whoops. There it is. This objective should be open now, but it may not be. One of my classes, this was scheduled for next week. The other class, it was scheduled for this week because y'all's tests are on different days from each other, of course, just to confuse my brain more. All right. Again, if you've got questions about the test, feel free to come by. I haven't seen the test, but I have seen the review for my 3:30 class, and it is a long but good review. If you can do the review, you can do the test. When she says she's going to pick 20 of those questions and change them slightly, she means just that. She will change the numbers, which might include changing a positive to a negative, and she might change the setting around a question, but the equation that the question would produce is going to be very similar. All right, so feel free to come by. I'm more than happy to talk about all of those. All right. That is all for this week, my lovely students. I may post next week's video early, just depends on how it goes, because it is long division with polynomials. I know I'm way too excited, but it's kind of fun. And I get to use all the colors. All right, ta-ta for now.